So hello, good evening, and welcome to this Audio Engineering Society UK webinar. Members get access to a global network of audio engineering professionals, discounts on conferences, access to the world-renowned AES journal, and many more benefits. This event is open to non-members as well as members, so if you're not a member, please head over to aes.org to find out more and consider joining us. So now for tonight's event. I'm delighted to welcome Basil Woods, a machine learning engineer and founder of AudioStrip, an AI music technology company specialising in music source separation. In tonight's talk, Basil will explore how modern machine learning has transformed automatic stem separation, the process of isolating individual instruments from a mixed recording. He'll cover the core challenges of source separation, the AI breakthroughs that made this high-quality separation possible, applications in music production, and the technology powering AudioStrip. Basil has led multiple funded research projects in collaboration with the Centre for Digital Music at Queen Mary University London, including an Innovate UK grant developing state-of-the-art AI systems for stem separation. His work sits at the intersection of cutting-edge research and real-world application, translating the latest advances in machine learning into practical tools for music producers and engineers. If you have any questions during Basil's talk, please use the Q&A button at the bottom of the Zoom window, and we'll get to those at the end. This event is being recorded and will be going up on our YouTube channel, AES UK section, all one word. So that's enough for me. It's time for me to welcome our speaker, Basil Woods.
Thank you, Neil, for the intro. And good evening or good morning or good afternoon to everyone, depending on where you are. Let me just share my screen. Okay, I'm sharing my screen now, so I'm assuming everyone can see it unless I hear otherwise. This talk is using ML for stem separation. And as Neil's already said, I'm Basil. My skill set is ML engineering. My background is I did a maths degree from Cambridge University and then have been working in ML for around 10 years after that. As Neil said, over the 10 years, my goal has really been utilizing cutting edge ML breakthroughs to build software and applications for the real world. This is sort of surrounding my work at AudioStrip. So AudioStrip is a music source separation company I founded a few years ago now. And basically we build technology that allows users to separate the stems from any song. I guess one of the most interesting things that's happened recently was us being one of only 5 companies to win Innovate UK grant in the music AI space. So before I begin, I just want to make it clear, I'm a machine learning person who's always been interested in sort of making music, and this is how I sort of got into the area of music source separation. So ML first, applying that to music rather than say music first and then learning ML. Let me sort of begin the main slides. Okay, so I'm sure most of you here know what audio source separation is, but let's set the scene just so everyone's on equal footing. So I guess audio source separation very simply is given an input mixture, can I break it down into the individual audio components? I guess the term, the cocktail party problem, was coined in the 50s, which was a term based on someone noticing that actually when we're in a crowded environment and we're just trying to focus on the voice of the person we're sitting next to have a conversation, our ears are naturally very, very good at separating out the speech they're saying from all the background noise in the background. You can imagine you're in a restaurant, there might be music in the background, there might be other people chattering, there might be plates smashing, hopefully not. And our ears naturally can focus on the person we're sitting next to and basically recover what is the speech audio that they're sort of talking. I guess audio source separation sort of spans a bit more than just that cocktail party problem, though, where in that problem we consider there always just being one source, i.e. the speech of the person talking, and everything else is background noise, something to be removed and discarded. I guess audio source separation spans lots of areas where we actually may want multiple sources. So for example, in this diagram, we've got, like, say, a mixture, a song with vocals, bass, and drums. And you could imagine someone actually wants vocals, all of those signals, that vocals, bass, and drums. They don't want anything discarded, and there's more than one source we care about. And I should mention, although people do say the human ear is naturally really good at this, I think one thing to note is, at least in my experience, when I'm speaking to a friend in a restaurant, though I can isolate out exactly what they're saying, it doesn't cleanly remove all of the stuff in the background. There is still some like background murmur there. So potentially differences in terms of how do we cleanly and absolutely remove everything else apart from what we care about. Okay, so with that definition of audio source separation, if we think about music source separation, why would we care about that? And so I've listed sort of 4 reasons why we might care about this. This is based on the sort of users we speak with and where they've found benefit from music source separation. So I guess the first bucket, you've sort of got the remixing and DJs. So a DJ might be playing a live set, and the really skilled DJs are really skilled at transitioning from one song to another seamlessly. And, you know, there's basic ways of doing this, like maybe just matching the BPMs or ensuring that the keys are roughly going to match. But from speaking to really experienced DJs, what you find is they do want some control of isolating certain parts of song A and isolating certain parts of song B. Otherwise, you could imagine cymbals from song A and cymbals of song B are going to clash as they're played over the top of each other. So you might want to fade the cymbals on one out and fade the other song in. Then we've got remastering. And so this is really big music licensing companies or independent artists who want to remaster a song they've got. And this is, I think we've seen this a lot where there's certain songs we love and someone comes up with the idea, or maybe I shouldn't be so cynical, but let's find new opportunity of making more money by creating a remaster. But what you actually find is the music labels don't keep hold of the stems of their old works. So it's actually incredibly hard to make a remaster when all you have is the final mastered versions. And then education. This one's quite interesting, where lots of people find that if there's a song they really like or a song they're trying to learn, by just isolating, say, the guitar, for example, it's much easier to follow exactly what's going on. And then a really interesting one I found was this rediscover one, where it's lots of times users will come to you with really like personal stories of maybe their brother, him and his brother used to love making songs when they were younger. They have old recordings of it. His brother had an amazing voice he loved to capture, but when he plays back the old tracks, they're maybe the audio quality is really bad. There's lots of background noise. It just doesn't sound very good. And maybe his brother since passed, and he sort of wants to do something with the original vocals he had of that track. And without technology like this, it would be impossible to recover those old damaged vocals from an old track. Okay, so I guess now we've sort of mentioned what audio source separation is and maybe why you want to do it. How was it done historically before deep learning? So I guess the main way just before deep learning was this method called NMF. You have to bear with me. This method is a bit before my own time. So I'm more explaining what I know of it rather than having used this method personally. But the idea is we take an input spectrogram, and we're saying we're proposing this input spectrogram can be broken down into distinct atoms, which we can sort of think about as the individual sources. And if we have a method that can break it down into atoms, and then over time tell us, say, the intensity of that atom over time, as well as model what the frequency distribution is for each individual atom, then we should be able to break down this mixture spectrogram into this can't read it, fixed spectral atoms matrix. And I guess when this each atom is active matrix. So this was a really bad technology, as in it was the best they had at the time, which was around 2012. But the key problems with this were, number one, it was unsupervised, i.e. you couldn't define what the atoms were. You sort of had this mathematical model that would just throw out atoms it thinks belongs in this mix. And so, for example, if you did want vocals, bass, and drums, there's no way of telling this model that's what you want. You could end up getting some incoherent mess for atom one. Atom two might be a mix of drums and bass. It might even think that an atom is just an entire frequency band, and in which case it's quite useless. So yeah, the fact it was unsupervised made it really hard to get clean stems that you actually cared about. And then the second big problem is the way this is modeled is way too simple. So the assumptions it's making is that each atom, or for simplicity in this talk, let's say each instrument, can be modeled as a constant frequency distribution. So for example, you can see this sort of, in this W matrix, you can sort of see this green column at the first green column, and you could imagine that might be the guitar, spectral distribution. And what this model is saying, that anywhere there's a guitar, it follows that exact same frequency distribution in time, just at different amplitudes or different loudnesses, which doesn't make sense, right? The tone of the guitar is going to change over time and things like this. So yeah, naturally, this came up with bad results, but sometimes you could just about figure out what the atoms were, and it would sort of somewhat split it apart. So yeah, then sort of the introduction of deep learning sort of became a huge thing. And I guess the remainder of my talk is sort of talking about, number one, what is deep learning? What are the methods in deep learning? And how have these methods in deep learning enabled music source separation to get much better? So just for anyone who's not familiar with deep learning, at a very high level, it's a mindset shift from, say, how you would have done traditional music information retrieval, where instead of having, say, a specialist in audio who maybe uses their own intuitions and insights to create mathematical models they think can perform whatever task they want. For example, this NMF model, music source separation, you instead generate a large network, and you basically say to the network, I'm going to feed you a bunch of training data. You learn the pattern for me. I may not give you any insights as an audio specialist as to how best model this, but I'm hoping if I give you enough data and if I make my neural network large enough, you'll sort of learn it yourself. And yeah, so this means we have a training set, a deep architecture, and some way of evaluating. We need to know how well the deep learning model is actually done. In music source separation, we use SDR, which is the signal to distortion ratio, with the formula measured there. And that's basically telling us how much, basically it's a power ratio, a logarithmic power ratio of the signal over the error, i.e. the predicted signal minus the real signal of the stem. So yeah, that's how deep learning comes in. So before I dive deep into the ML methods, I just want to again mention maybe why music source separation is hard and why it's hard even with deep learning. And I've sort of put here as a subtitle, and even harder than speech. So like firstly, like the first point, which maybe emphasizes even harder than speech, is again with speech, there's likely just one source you're interested in separating. It might be my voice in the Zoom call over the background noise in the room I'm in, and I'm sure Zoom are using speech separation to remove background noise. But if you think about it, like the frequency distribution of the background noise is likely going to be much, much different to my own voice, where the nature of music is there is going to be lots and lots of, well, maybe not lots and lots, but there will be instruments that share the same acoustic space, i.e. they have the same, they have overlapping frequencies they're going to overlap at, and they're going to operate at similar pans. So yeah, the nature of music means there's going to be lots of sources that overlap in the frequency space and the pan space. Additionally, in music source separation, it's been really hard in research to find large data sets. And in fact, even today, most research papers published use no more than 150 songs to train their models. And for those of you that don't know about how much data is needed to train really large deep learning models, you'd like image processing, you'd likely want millions of images. And I guess with like LLMs, we know they've sort of been trained on the whole internet. So yeah, tiny data sets. Then in music and audio, but I guess to a lesser degree, the sequences are incredibly large. So I guess music is generally 44.1 thousand samples per second. And if you compare this to text, let's say what's ChatGPT is doing, I doubt most of us prompt more than a few hundred words in a prompt, and there's around 3 tokens per word. So you're going from maybe ChatGPT having to deal with sequences of 300 sort of measurements to here having 44.1 thousand a second, which is challenging. I guess another one that makes it quite hard actually is the high quality expectations from the end users. So again, I talk about speech separation, where likely, again, the Zoom call is doing some sort of speech separation or background removal. And I guess all they care about is are the words I'm saying intelligible? They probably care less about the quality. They probably care less about the listening experience. But if you're a music producer, or if you're a DJ, of course you care about how the music sounds. It has to sound as perfect as possible. So the standards for music separation are going to be harder. I guess a few other reasons before I go to the next slide, because I could sort of talk on and on about this. But I guess the fact that minor distortions in a few samples of an audio track usually are perceptible to the ear as a sort of clicking noise means that if the ML model gets a few samples wrong, it's likely ruined the track, i.e. for someone that cares about listening quality, if they hear a few clicks, it probably isn't a good experience. Maybe one more before I go to the next slide, which is there's actually no well, I don't know of any good mathematical way to evaluate separation quality. So I know on a prior slide, I mentioned we use SDR, signal to distortion ratio, which is mathematical way of saying how much error is there in this waveform versus this one. But that doesn't really map very well onto what our ears actually hear perceptually. And I'll talk about this in a few slides down. But what you do find is models with higher SDRs, i.e. mathematically most similar waveforms, actually can sometimes sound worse than models that have less SDR, i.e. more imperfect waveform mathematically. So that's a real challenge, not having a consistent metric to know if one model is better than the other. Okay, so now I've talked a bit at length about music separation, and maybe a bit about deep learning has sort of leaked into music separation. I'll spend a few slides now on really talking about first of the basics of neural networks, how they work, and then how, as new discoveries in deep learning came in, how that affected what the models people built music separation with changed over time. So yeah, very simply, you've probably seen diagrams like this before, where a neural network is a series of nodes organized in layers. And you see at the leftmost side, you have input nodes. The most right side, you have output nodes. And the idea is, given an input, you pass it through the input, and data flows through each subsequent layer until it gets to the output. In this example, there's only one hidden layer, the one in green. But most networks will have hundreds, thousands, and potentially millions of layers in between. I guess what you notice is sort of each node in a prior layer is connected to every single node in the next layer, which basically means but each prior node has a way of communicating with every single node on the next layer. And yet, without going into the mathematical details, why are neural networks actually useful? Why is there any hype around neural networks in the first place? I guess at a very high level, neural networks have been shown to be able to model any single function you can write in logic, given you give it the correct weights. The weights are sort of, I guess, will be numbers on the edges, which are multiplying individual nodes by to get to the next layer. Anyway, so basically, what I mean when I say that is, let's take music source separation, for example. If there exists a perfect logical function or perfect logic to separate stems, it means that there exists a neural network where, given the right input parameters, it will be able to model that. So this is why they're broadly used. They can model anything. Again, the caveat is, can you find the correct input parameters? And finding the correct, not input parameters, sorry, weight parameters. And finding the correct weight parameters is the hard part of machine learning. And without going too technically, we have non-perfect ways of trying to find the optimal weights, which is basically we have some sort of error function, something we want to minimize, and we are basically going to try and figure out what parameters will minimize this objective function. So in a way, you could say, if people don't do it, and I don't think you can, but you could imagine SDR being our objective function. That's maybe negative SDR, because we want to maximize SDR, but if we were to minimize it, we might do the negative version of that. But so you could imagine that's an objective function we're trying to minimize. What weights can I use that are going to give me the smallest possible value? So sort of finding this global minima in whatever curve the weight space happens to be. This image is one-dimensional, but clearly in the real world, it'll be hundreds, thousands, millions of dimensions. Cool. So that's a bit of the basics of of artificial neural networks. Now I'm just going to introduce convolutional neural networks, and then I'm going to show how convolutional neural networks were initially applied to music source separation. So I know it's a really complex diagram. I think we can ignore most of the details, and I'll sort of walk you through the parts that really matter. So if we see there's a picture of a zebra, and then you've sort of got a stack of squares to the right of it, and then another stack of squares, and another stack of squares. Convolutional neural networks basically the same pattern we saw with artificial neural networks, where we have, say, an input layer, and then a series of hidden or intermediate layers, and then output layers. And here the layers are basically two-dimensional representations. So the input layer is a two-dimensional representation of a giraffe. Then there's a layer after that, which sort of, again, data flows from the input layer to the next layer to try and create a more dense representation of the information. You pass through layer upon layer upon layer upon layer until eventually you'll output some sort of prediction. In this example, we're predicting the probability of it being a horse versus a zebra or a dog. So I think the main thing to take from CNNs and how they're different and sort of why they grew so much traction is, well, basically it's because they work very, very well with images. So if you've ever used image detection technology or have seen it being used in your app, it's very likely it's using a CNN. And the reason it works so well is in artificial neural networks, we saw that each node connected to every single node on the next layer, and each node in that layer was connected to every single node in the prior layer. CNNs actually doesn't do that. You see, there's this square around the zebra's leg called the kernel, and that's basically a square that's just going to scan across the image. So it'll start in like the top left, go all the way to the right, then down and go to the right, and basically scan over the whole image. And the receptive field, i.e. what the next layer sees, is actually just anything in that square. So it doesn't use every single pixel to predict the next layer. It only uses the pixels within a given square. And you may think, well, why is that good? That seems like you're using less information. Wouldn't it be better just to use the whole zebra for every single pixel in a more dense representation? But actually what you find is because there's far less connections between a node in layer n and n-1, it makes it much easier for the model to learn and much more efficient, because you've sort of reduced the feature space of all the possible like combinations of weights you could use. So you've simplified a really hard complicated problem into a more simpler one that seems more intuitive for images. And then sort of the second reason why that's actually quite useful is this square that sort of scans over the whole image is using the same weight parameters on every single part of that image. And conceptually or intuitively, you can think of it as a given square's job is to detect a specific characteristic of the image, and it will only look at that specific square. What this means is, for example, you could imagine this square over its leg. Maybe it's a leg detector. Again, it goes through every single square of the image, starting from top left and eventually getting to the bottom right. And each square will detect, it will detect, is there a leg or not? And again, that's useful because number one, it reduces the number of parameters and makes it a much easier space to learn from. But it's also using the intrinsic property of images, where if I see a leg in the top left, if I've say got some sort of model that can detect a leg in the top left or any image, that same detector is likely going to work, whether that's legs in the top left, top right, middle left, bottom right, or whatever. So simpler space, but also using this intrinsic property of images is once you've got some model that can learn, is there a leg in this square? You can sort of pass it around the whole image and find all the legs in that image. And that's a really important, that last point is really important, especially when we're applying to music source separation, as to why it doesn't work so well with music source separation. So yeah, let me move to CNNs in music source separation. So here, again, this was really early attempts, and they weren't this simplistic for the purpose, but for the purposes of demonstrating, I came up with a simplified way of looking at it. The early days, we would, in music source separation deep learning, our input is sort of a spectrogram, and our output is going to be a spectrogram, i.e. Input mixture spectrogram, and then output source spectrogram. So for example, vocals spectrogram. And if you're detecting 5 instruments, you'd have 5 output spectrograms. And so, yeah, just like we saw before, you see this shared filter, again, simplified here, but basically like a square that you see scans across the whole image looking for a specific pattern. And you see the output of that is if it matches the pattern it looks for, it sort of fires on the output. And yeah, again, simplified, but you could imagine doing this a bunch of times, chaining these together. You could imagine at the end, the output you get is a spectrogram, which you can do some post-processing on to get your output source. So yeah, so why doesn't that actually work very well in music source separation? And it's basically the reason I said it was so good for images is why it's so, well, I wouldn't say so bad, but maybe doesn't work so well on audio, which is the reason we could use this shared parameter, this shared detector that's going to look for a specific pattern. Again, a pattern it's learned itself through training data. Yeah, it's going to look through this pattern through every sort of square of my input image and find if that exists. And because a smiley face looks exactly the same if it's in the top left as the bottom right to the middle to wherever, we're happy saying that this detector does the job of detecting a smiley face. I guess the problem with spectrograms is they're not position invariant, i.e. if you have a really good detector to detect guitars at the higher frequencies, it's probably going to be very, very bad at detecting guitars in the lower frequencies because the patterns aren't the same. You can't just translate a spectrogram and sort of get the same audio or similar audio out of it. And then another thing this isn't so great at is it's not very good at long range dependencies. Oh, sorry, I'll just get a glass of water. Yeah, so what I mean by long range dependencies is, again, we see with artificial neural networks, we sort of use every single node of the prior layer to inform the next layer. But we said in CNNs, we're just going to restrict ourselves to squares. So sort of each square in our output has only seen a sub-selection of squares in our input. What this means is it's restricted at the patterns it can see. If it, for example, it can't use the whole frequency distribution, because in this example, you see it's only actually seen 2 frequency bins here. So that sort of restricts the sort of patterns it can learn. So yeah, that's a bit about how CNN sort of came into play, and the main disadvantages, which is number one, you can't share a feature detector in one position, the spectrogram, with another position, because again, frequencies aren't position invariant. And number two, it's very bad at, it doesn't allow long range dependency. So if you wanted to use the whole frequency range in order to make a prediction, you're unable to do that unless you want to do some extra smart things on top of that. Okay, so now I'm going to talk about UNets, and UNets are quite interesting because for the longest time that they are what got state-of-the-art results. And I think even today, most people are using a UNet in music source separation, although adding more fancy elements to it, which we will discuss in a moment. So again, I'm sorry, with the really complex diagrams, it's hard to get good pictures of sort of neural net architectures, because they tend to be very academic. But if I could break this down simply, a UNet is basically it's just a collection of convolutional steps. A convolutional step, again, is what we saw with the CNNs, i.e. like a square that scans the whole input image and then passes an output layer. So sort of every thin line here is just a different convolution. And so we just have loads of convolutions in sequence. The idea with the UNet is it's what we call an encoder-decoder network, where each level, you see it starts at like the input level, and then it does a few convolutions, keeping the same image size before it then passes to a smaller, or goes down one level to do convolutions on a smaller image, and then that does a few convolutions and then goes down to a smaller image, and so on and so forth. So again, a bunch of convolutions to top level, then it sort of compresses the size, does a bunch more, compresses a bunch more, and so on and so forth, until we get to the bottom layer where it's really, really thin. And then we've got this decoder part where we're going to blow this back up into to a proper image again. So again, a bunch of convolutions, then we sort of resize the image, blow it up a bit, a few more convolutions, blow it up, so on and so forth, until we get to the original image size. You might ask, like, why would you do that? That just seems complicated. So the intuition behind it is the encoder is sort of trying to compress semantic information in the image. And then the decoder sort of, once it has that semantic information, its purpose is to sort of, I guess, generate the output image from that, i.e. create the spatial information from the compressed information. So to explain roughly what that might mean is, say for example, so yeah, here's two examples on the right, which is what UNets are traditionally used for. So self-driving cars and maybe medical imaging. And a UNet basically allows you to create an image where every single pixel is classified. So like, let's say in this picture of someone's head, you could imagine every pixel here is classified as 0, apart from this red area, which might be classified as 1, and it's sort of classifying. I think in this case, it might have been parts of the brain where there might be a tumor or something like this. And then this image of this road, you see every single pixel is colored, and that's based on its classification. So likely one color is classifying whether it's a road, then you see this dark blue consistently classifies if it's a car, and this red classifies if it's a person, and so on and so forth. So yeah, this is what UNets are traditionally used for sort of classifying every given pixel. And again, so why do we compress and then blow up? So you could imagine for to create this segmentation of, let's say, this driving scene, the end goal is every pixel, you need to know whether it's a car, road, or person, or let's say a traffic light. To do that, we first need to know everything about the scene as possible. So that's sort of the encoder's job. Again, it learns itself, so you don't know exactly what it's doing, but you can think it's probably compressing it eventually to saying something like, there's traffic lights in the top left, there's a car in the middle, there's around a few dozen people, some on the left and some on the right. And basically compressing down everything important in the scene, probably with some indication roughly spatially where it is. But also, obviously, if it's compressed to a tiny number of pixels, it can't say anything more than, let's say, top left, top right, middle left, middle right, so on and so forth. So yeah, that will compress everything you need to know about this image to classify it. And then the decoder's job is now now it knows, basically it now knows where everything is and everything exists in the image. Its job is basically just to figure out spatially where that is. And so that's why it's taking the compressed information and sort of trying to blow it up. And then you see these skip connections, these arrows from left to right. And that's allowing information to flow from the corresponding level of the encoder, which will give it the exact pixels it needs to know about. So I think the most intuitive one to explain is maybe the top level. So the input skip connection to the output. If it only got information from the lower level decoder step, it has no idea exactly what pixel position, the car actually is. But because it has access information flow from the input, which obviously has every single pixel, that information can flow as to, the exact, pixels which the car actually occupies. So yeah, this is UNets, and again, what they're used classically for image segmentation, classify every single pixel, and they work by sort of encoding the semantic information and then blowing it up to create a new image. Now we'll see how they're used in music source separation, maybe naively at first. Come on. Yeah, so I get, so again, this is like a very naive approach. So I flatten the U-net, so it's more of like a line net. But you could imagine if I just drag that bottleneck layer down, you'd have the same U shape. So again, you can imagine just having an input spectrogram to provide the spatial information. And then again, you could imagine classifying every single, let's say, time frequency bin as whether it contains vocals or not. So again, for a simple example, it's like the 1 or the 0. Once you have whether there's a vocal in every sort of time frequency bin, you've essentially got your output vocal spectrogram. There's a bit more detail, but I won't go into them here. So why is this naive, or the downfall? So yeah, same downfalls as CNNs, because this relies on CNNs, which is they're not spectrograms aren't position invariant. So because it's still built on using CNNs, which only see certain sub-squares at a time, the same filter it might be using to detect the guitar in the high frequencies would be the same as the low frequencies, which again doesn't really work and can't generalize. And then again, they're not very good on long range dependencies, because each subsquare only sees a narrow field. So for example, if you wanted to access the whole frequency distribution, you can't do it basically, or you can, but more complicated. I guess what was naive about these early approaches as well was when they were generating these spectrograms, they were just generating the magnitude spectrograms, which meant that you lost the phase information. And don't know if I guess you've probably listened to audio where I guess the frequencies are out of phase, but it doesn't sound nice. It sounds muddy, and you clearly wouldn't be able to use this for professional music cases. So we created an artificial limit on ourselves by using magnitude spectrograms, where the best we could possibly do would be a mess, basically. I.e. doesn't sound very nice, or not that similar to the original source. So that's UNets in music source separation. And then there's sort of like the use of RNNs in music source separation. So first, just to introduce again very simply what an RNN is. RNNs are basically sequence models, which the problem is, imagine you have a sequence of inputs and you want a sequence of outputs. This is sort of model you would need to use, because sequences can have an unbounded length. I think if you saw the artificial neural network image a few slides back, you saw that when we define the architecture, we have to hard code exactly how many output nodes we have. So in that example, it was 2. And it means we can't define an output sequence of any more than 2. So with RNNs, it allows us, it gives us a model where we can train once, and now for any unbounded input sequence length, we can also create an unbounded output sequence length. And again, it's all neural network. So this hidden layer, although it's a square, you can imagine it's a layer of nodes which are fully connected to the prior node and fully connected to the output node. And yeah, I guess maybe places where you've probably been, well, maybe not so much now, but places where these would have been used a lot would be text translation, right? So maybe you put an input sequence of words into a model, like, hello, my name is Basil. And then the model will output a sequence translated, let's say, into French. And I'm not going to attempt to translate French on the spot, but I'm sure some of you could do that in your head. And I guess one way more topical now is Suno, right? The input sequence is a sequence of words, and the output sequence is, I guess, a sequence of well, music. Audio is a sequence of samples, right? So yeah, I think these days sequence models are sort of way more useful. Might be a bit of an overstatement, but sequence, most of the places when we think about AI is sequence models, where I can put any unbounded text input and it can give me any unbounded text or audio or video output, for example. So again, a very naive approach of how you might use an RNN in music source separation. So again, we started with an input spectrogram. We sort of chopped it up into the individual timestamps. And at each timestamp, we put the whole frequency distribution at that time step. And again, information, data flows from left till right until we terminate, i.e. there's no more outputs to output. So here, again, the input is probably a mixture and the output might be vocal spectrogram. And then again, at the end, you sort of would just concatenate this together. The main drawbacks for RNNs in music source separation were it's very slow to train. And this is because you see how information flows. You can only each subsequent layer can only be calculated once you've got the layer before that. And that means to get a value from the farmost right layer, you would have first had to have put it through the first one, then the second, and the third, and the fourth, and the fifth, and so on. So it couldn't be parallelized. You had to sort of do sequential stuff to get your output values and also to run your training algorithm. It also turns out to be not very good for long sequences. And the reason being is, again, you see how information flows. Each layer only flows information to the next layer, which means it's very hard for any information from this first layer to still have gotten through to the rightmost layer. If you can imagine, each sort of layer is passing in important semantic information. By the time it's gone through, say, 6 filters, there's probably little left of the first layer left, and this is really problematic for music sequences, right? Because they are huge sequences, so information from the start of the sequence is likely to be lost. So yeah, this is where I guess transformers came in sort of. This was an explosion where suddenly these models were getting really powerful, and this sort of coincides where transformers have made things powerful in other domains as well. So in case you're not aware, transformers is actually the T in GPT, i.e. ChatGPT, and yeah, now all these AI companies are basically relying on the invention of or the discovery of the transformer, and that's where how all of this, I guess, incredibly powerful AI has come from. Without going into the architecture, I'll just speak about what it solved, that the RNNs couldn't do, which number one was these can be parallelized. Training here can be parallelized, so it's a lot more fast and efficient to train, because as you see, again, it's a naive illustration. But because to get to each sequence output, we actually don't rely on the output of the prior step. So it means we can actually generate all of these in parallel and also train them in parallel. It's also in certain cases, it's faster to do inference, i.e., before we were talking about the speed of training, but let's say when I'm typing, hello, what's the weather like, to ChatGPT, how fast do I get an output at? And transformers are much faster at doing this. And also they solve this problem where they can't forget the start of the sequence, because each output sequence step has access to every single input sequence step. So if there's important information at the very first time step in the spectrogram, it has access to that. That's a bit about, I guess, how transformers changed everything. I guess the caveats, and so they did all this great stuff. What are maybe the drawbacks from them? I guess number one is they're more data hungry, i.e. they require much more training data to get good results. But also, sort of a blessing and a curse, it removed the ceiling of the performance you could get out of deep learning just by making the network bigger. So before transformers, let's say with RNNs and prior models, you might think, why don't I just add more and more layers until I have a huge thing and it can learn really complex problems and get great performance? Well, actually, you find that there's a cap at some size. These models stop getting any better. But with transformers, actually, there almost is no cap. The more complex you make it, the more training data you give it, the better they get. And I guess this is another really key property as to why I guess ChatGPT and stuff, and maybe Suno have gotten so powerful. They make the architectures bigger, more powerful, and throw more training data, and they'll get better. I won't go through this complex diagram, but if anyone's interested, I can share with them. To circle back into how has the technology progressed over time, I guess here's sort of like a slide of maybe within the last 15 years, how with ML advances, music source separation has got more powerful. So again, we started with naive spectrogram masks, which were magnitude spectrograms, and obviously I mentioned before have a ceiling because we've removed the phase information. The best we can get is a really bad separation. And then there was sort of like a point in time where people said, actually, maybe we should include make it phase aware. Let's use the complex spectrogram. Then there was a period where we were using a hybrid of waveform and spectrogram models. I haven't really talked much about waveform models because I think no one really uses them anymore. But there was a time where, again, maybe due to the infancy of the technology, they found that if you sort of build a waveform model, a spectrum, i.e. a model that goes from mixture waveform and outputs n source waveforms, and another model, which is like the ones I've shown you, where you go from an input spectrogram to n output spectrogram sources. So you have two models there, and you sort of average the results, or you combine them. But yeah, we don't do that so much now. And then I guess this was sort of the solution to something I sort of kept mentioning a lot, which was a naive implementation of of a CNN where it's using the same feature patterns for, let's say, the top left of the spectrogram to the bottom right. And eventually, and this actually improved performance a whole lot, is if you actually just separate out your spectrogram into frequency bands. So maybe a simple example might be you chop it in thirds and you say this range is high frequency bands, this one's medium, and this one's low. And then so you chop them out and you basically have say different filters or different kernels looking at different patterns per frequency band. And as you can imagine, that does improve it a lot, because now you've removed this limit of having to assume what a guitar looks like in a high frequency is the same as a low frequency. And then transformers, as I've just mentioned, it sort of made training really, really fast. It made it able to access like the full time range. So long range dependencies were possible. And now you throw more and more data at it, and you make bigger and bigger networks, and you get better and better models. So that sort of some people sort of said music source separation is a solved problem once transformers came back. I sort of disagree with that. So I've put this next step, which is efficiency and speed, which, yes, you technically can create a huge transformer with loads and loads of data. But number one, do you have that much data? And number two, is that profitable? If you're using hundreds of GPUs and it's taking hours of processing for a user to get their mix back, is that really the goal? I don't think so. So I think lots of people are focusing on efficiency. But very, very quickly, because I know I'm sort of touching the end of my allotted time, I'll talk about a different area, which I personally think is much more valuable than efficiency and speed, but certainly lends into it. So I guess how we're looking at this is, again, we have lost stems, a bunch of mixes where we want the output stems. Currently, most of the research and most commercial products will just output 4 output stems: bass, drums, vocals, and then an ugly one called other. But we actually think we want to be able to separate an arbitrary number of stems, i.e. an arbitrary number of instruments at high quality. If I skip over how we do this practically, maybe to move on to actually a high-level idea of how we're thinking about this is, again, you sort of see this UNet structure, which works sort of well. And again, we're sort of doing this band split where I guess it's a poor diagram because it's transformed to a spectrogram, then we're splitting it into bands, so different patterns can be learned on high, medium, and low frequencies. But what we think is more useful, rather than hard coding our model works on instrument A, B, C, D, is creating a model where, given at inference time, i.e. anyone that uses that application, if they could just provide a sample of the audio they're looking for, if our model can figure out what that instrument is and separate that from the audio, we think that's way more powerful. And the reasons for that are, I guess, number one, it makes training more scalable. Before, if you wanted to train let's say you wanted to have a saxophone model, you now have to train a whole new model that can run on saxophone. But I guess with this approach, you sort of train once on every instrument, and then at inference, even if it hasn't heard that exact audio sample, because it's learned what, say, instruments sound like, it can sort of figure out, sort of listen to your sample and find in the audio the most sort of similar instrument to that sample and separate it. The other really interesting thing that this solves, which probably you wouldn't think about if you're on the user-facing side, it's actually really hard to create labeled data sets of instruments. My personal feeling is why the research community settled on or one of the reasons why I said on vocals, bass and drums is it's very, very easy to define vocals, bass and drums. Maybe it gets a bit harder with electronic music, but you probably would just classify a bass synth or an 808 as a bass, and again, drums, drum machines will be classified as drums. But when you expand out from that, other instruments become very, very hard to come up with definitions. For example, let's take a piano. So I guess maybe when I say piano, most of us are thinking classical piano, but shouldn't I include an electric piano? But then I guess if I choose an electric piano, shouldn't I include some of the synths that sound a bit like a piano? Then if I use synths, there's a lot of synth sounds that don't sound like pianos. And now what if I want to have a synth label as well? I already labeled that synth piano as piano. It can't be synth piano and synth. Now there's like whatever synth synth strings. Is that synth or is that strings? So yeah, I think it solves an interesting problem here where we don't actually have to partition all instruments cleanly, because at inference time, someone can just the model will listen to that audio sample and figure out which instrument in the mixture most matches this one. So yeah, we got really good results on this state of the art. I'll skip over this, but it's a hard problem making these things run profitably because you have to use GPUs and they're expensive and things like this. A bit of what our tool looks like. I'll probably skip over listening examples just due to time, but I can pass some examples of what the separation quality sounds like if anyone's interested afterwards. And yeah, so again, it's sort of the same diagram, but here's what I'm saying. We sort of went from NMF, from spectrogram masks to complex and hybrid spectrograms to splitting in bands to transformers. And now it's efficiency, but I also think query, like given an input audio sample, can you separate? Can the ML model listen to that sample and figure it out rather than having to pre-label and pre-train every single instrument? So coming towards the end now, but why do you care about music source separation? Because we're in this world of Suno, and that's sort of the music AI everyone's talking about. Well, I guess I'll just give the three reasons here, which is even in a world where people don't make music, which I think is unlikely, there's people are trying to now build technology, say, where you're given a song, can you make an adaptive remix? I.e., the listening experience you get when you're listening to a song is completely different to mine. This created on the fly. Well, to do that, that technology would have to, in the background, separate it into the stems so it can sort of remix and play with those stems in some way. Yeah, I guess other applications you could use to generative music. I know, for example, Suno, if you create a song, you can get the stems back, but actually, because the model just creates the mixture itself, it actually uses one generative model to create the song. Then it's using a source separation model to separate. So even Suno using technology like this, when people are asking for the stems back to remix. And I'll just close on who's using it. A bit of a shameless plug, but hey. So yeah, so the source separation quality compared to your competitors is like night and day. These saxophone stems are amazing. If I hadn't told the team they were separated, they wouldn't have known. That's from an award-winning composer and member of BAFTA. And by far the cleanest and most usable results of any extraction tool I've used. So yeah, that's it. Thank you. And apologies, I went a bit over time. I know some of you probably have schedules.
Well, thank you, Basil. That was a fascinating talk. Thank you. Great. So yeah, let's have a look. We do have some questions. Let's have a look in the Q&A. Yes, so let's start off. There's a question from Caleb, I think fairly early on in your slide deck, you talked about complex relationships in a slide. Just wondered what I think it was the one before why music separation is hard.
This
Somewhere
slide.
about there, yeah. So that there was there was a question about what do complex relationships mean in the previous slide.
Oh, this one. Okay, captures complex relationship. So what I think I meant here is, again, before deep learning, it was like music information retrieval. Most fields, you really needed to have an expert to try and reason about what's in the spectrogram. How can I separate it? Where in the spectrogram is it? May a guitar be, and how does it relate with other instruments? I think what I meant here is these models can capture these complex relationships themselves, and you don't need an expert to do it. But also, it probably will capture patterns you wouldn't have thought of, because it's really looking at the lowest granular level of, say, how different frequency time bins relate. And I doubt any of us are looking at whatever pixel 3.5 and how does it compare to 100, 125 or something like that.
Okay, cool. Well, since this is the Audio Engineering Society, there's we'd love to actually hear what you're able to achieve.
Okay.
So
Okay.
let's go to the audio samples.
Okay, cool. Let me just change my shared screen. Any preference out of saxophone, drums, piano, or guitar, or I can just choose one myself?
Start with the mix, and we can have a listen to the stems and how good your system is able to separate them.
I'll start with, this is a mixture with a saxophone. Just need to. And then here is the saxophone removed, or saxophone. Maybe I like the one where we separate the drums. It's in the individual sort of drum components. This one will play.
You could be such an empty soul. Help me pack and you watch me go.
Okay, I think. And then here's the kick separated from that. It's probably hard to remember what the kick was like, but can you hear that? Then here's a snare from that same track. And here's the cymbals. I know we probably should have separated hi-hats from other cymbals, but this was easier to get working. I think it's buckling or something. But yeah. I think those are some examples.
Yeah. Could you do the cymbals again, but a bit louder so we can hear the?
Oh, I see.
What's also interesting is the silence between.
Yeah. So as you probably heard like a bit of bleeding of other drums there, but yeah, drums is definitely the hardest one to separate individual components from that. But yeah.
Okay, brilliant. Okay. So there's a question from Jerry saying it extracts the reverb and ambience as well. Would it be possible to sort of say, for example, delayed slapback delay?
No. So currently, oh yeah, sorry. What?
No, go on. Yeah.
Yeah. Sorry. Yeah. So currently, most models and ours does as well assume that the final mix is just the sum of the input sources. So you can imagine if you had vocals and you added effects, it can't undo the effects. There is some research in that area, but it tends to be a harder problem.
Okay, now getting back to the Q&A. Just a quick question from Dan. Are any of these examples available on your website?
I think on our blogs page, is there a way I can share some URLs with you, Neil, and you can distribute them?
Absolutely. What we'll do is when we put this talk together for a YouTube video, that will go on our YouTube channel, and any links to blogs, the company website, if we can put the slides up as well, then that will be really, really good. And we can, and so for everyone here who's interested can look that information up later on. Okay, so question back to Q&A. So question from Dan Foley. How well does current ML stem separation work when a song has doubled instruments or vocals? For example, Stevie Wonder does sort of doubles his vocals on a song, and if you've only got the master, how do you then separate that out?
Oh, so is the question when there's sort of two vocal tracks?
So if you've got one singer who then sort of sings a double like a harmony, are you able to separate out those individual tracks almost? Yeah.
So currently not. If the two singers were separate, we do have models that can sort of separate the lead singer from the backing singer, but sort of is working on identifying who the singer is. So if the same voice is doing two tracks, it would put them together in one output track. So currently not, but it seems like an interesting problem to solve.
Okay, question from John Grant. In a cocktail party, going back to one of your first slides, part of the filtering is partly spatial. So I can direct my hearing to the person in front, and so use the spatial information. Are you able to use spatial information at all? For example, in a stereo mix, that one instrumentalist may be on the right side, another instrumentalist on the left side.
Yeah. So we do use that. So we only support 2 channels. And how that works in practice is we have sort of a complex spectrogram for left audio channel and one for the right, and then you sort of combine them together. So in essence, you sort of got 4 spectrograms, the complex and I mean the imaginary and real for left and right. So we do model that in, but we don't use any more than 2 channels. Not sure how common that is, but yeah.
Okay, next. Yep, that's answered. There's a really cheeky question from Alexandra. You say it's hard to get training data for the models, but couldn't you just scrape lots of audio samples from YouTube?
Yeah. Okay, yeah. Interesting question. No, I don't.
Lawyer, I think is probably the.
I don't think. I don't think you should, especially the music industry aren't happy with not getting their compensation for the training data. So what we've found is we've had to partner with music licensing companies who will give us access to N,000 stems and us to process it. And I think that's the right way of doing it.
Yes, of course. Caleb was asking, would you be interested in training your AI model on a custom-built recording library of privately owned music?
Yeah, I guess it's an interesting request. I think, to answer the question directly, no, I haven't thought of doing that. I think the challenges of that would be, is there enough training data to train the model? I know I said traditionally in research, I've only used 150 songs. So yeah, if there was a private data set of 150 songs, we could probably train something. But the ones we're using in production now, as I said, are trained on thousands of songs. So have I thought about it? Not really. Do I think it's a good idea? Not to get the optimal performance, but it's probably possible, yeah.
Okay, let's back to the Q&A. There's a few more questions coming through. Interesting one from Flavio. So you've got the audio. What about, say, highly compressed audio, where you don't have much of a dynamic range? Does that make things better or worse?
Yeah, that's an interesting one. I don't think we've experimented with highly compressed audio. I guess for our use case, we've tended to find that the users using our service would have access to a good quality mixture. That's an interesting problem. I imagine if we wanted to make it work, we would want to ensure our training data set reflects all different ranges of how compressed the audio is, so it's seen all of them. But yeah, no, that's an interesting one, and yeah, I'll probably have a think about that after that, whether that's an interesting use case.
Yeah, interesting. Another interesting question this time from Jonathan. Do you use any of the data from clients using your work for stem splitting to then train any of your models?
Oh, no, we don't. So I'm pretty sure that's illegal or definitely morally questionable. So no, we delete all the audio after, when the client no longer needs it, it's automatically. Data we use for training is the data we've paid for from licenses.
Okay, so there's a clear separation between the data used for training and your paying clients' data.
Yeah, correct.
Okay, how else what have we got? There's interesting question from Daniel. With the new query retrieval method, is the network first trained as a normal source separator, and then when you want to use it for inference, you condition it with an example of whatever source you want extracted?
Yeah, you sort of got it right. I'll just maybe explain like the nuances. So so at train time, we do separate, let's say, this normal UNet, but we also inject at training time a specific audio sample we want it to separate and learn from. So you can imagine at training time, we say, here's a mixture of guitar, bass, and a bunch of other instruments. I'm going to give you a sample of a guitar, and you wanted to output the guitar stem, and you would compare that to the actual real guitar stem to see how well that works. So at training time, we do still inject the audio sample, but yeah, the idea at inference time is I guess pretty much the same thing. Yeah, you inject the audio as well as and it passes through the audio separation network. They do sort of happen together, both in training and inference, actually.
Okay, and I'm going to take the last question, another question from Jonathan. What songs are ideal for a data set and why?
Okay, yeah, interesting question. So I think the main thing, let's take the obvious one out. Like the data set there should be a lot of songs in the data set, obviously. Then I think you want a lot of variation. Well, I guess it depends on the application of your model. Like for us who are trying to build a model that quote unquote can separate any song, we want the distribution of the data we're training on to match the distribution of data people are going to put through our models, which is going to be any song you can conceive of, whether it's hip hop versus 60s rock versus whatever pop. So we need our data set to match that. I guess if you were building your own one and you said, I only care about separating 60s rock, all of your music would be 60s rock. It would get very good at that task. And you probably don't want to bias it with information of how whether 90s hip hop is mixed. I guess and a lot of data. Number two, match the distribution of the intended use case.
Okay, well, that's all the questions. I think that's, yes, coming up to time. So yes, it is my pleasure to say thank you very much to Basil for this fascinating talk and answering lots of questions. Thank you to everyone who attended, and especially for your questions. And thank you to the AES for providing with the resources for this. And yes, it just remains for me to say thank you to everyone for coming, and have a great morning, afternoon, evening, whatever. It's time for my dinner.
Yeah. And thank you for inviting me on, Neil. Thanks. And thanks for everyone for listening.